Welcome to the optical communication course. We study here that is about a transmission line, that model of a optical fiber here, and how your light is incident inside the optical fiber, and how your light is propagating through the fiber that we are learning today. So now we say that a core, optical fiber core, if you draw a diagram of a optical fiber, your optical fiber will be look like this one is nothing but a core of a optical fiber, and that is about your center of a fiber. Now this is of core, this is about a cladding, and outer layer is nothing but we can say it is about a jacket. Now right now we are not consider the jacket, we just consider this is nothing but a core here, okay, and this one is nothing but a cladding layer, okay, that is nothing but a cladding. Uh, Now when a light propagating through the fiber incident, okay, so in that case what happened? So at this boundaries condition means at the boundaries of a core and cladding, your light will be reflecting. Why this light will be reflecting? Because we have the index profile of this core. Okay, that is about we can say that index profile of a core. Okay, that is, we can say it is a high. Okay, high. And here for this, it is about a low profile index. That cladding has the low profile index, and a core has a high profile index. Now means index of refraction for this particular given core and cladding, if we calculate that, so it is nothing but what we can say here. We say supposed to be it is about a n2 and this is about a n1. In that case, for a given particular fiber, n2 is greater than n1. Now a light incident, okay, inside this particular fiber. So at the boundary between that core and cladding, so what happened because of that index of proof that that refractive index of this particular core and a cladding, if you see that, yeah, that cladding has a low index of a refraction. Okay, refractive index is low, so that's why it will not propagating, your light will not propagating inside this particular fiber. And again need to maintain that angle. Which angle? That is angle of what you can say, that is about your that incident light angle. If that incident light angle, that whatever we say is right now, suppose I am saying it is about a phi now, or phi 1, okay, so that phi 1 or a phi is greater than the critical angle. It is to be greater than the critical angle. Then and then your light is propagating, means your light will be, whatever the incident ray will be there, it will be reflecting from that. Now then it will reach to this particular boundary, okay, it will reach to this particular boundary, and again we can consider that this phi, okay, it is to be greater than that critical angle. Then and then it will be reflected. So means your light will be reflecting throughout this particular fiber, okay, throughout this particular fiber. So why it is reflecting? Because that incident ray, this is about your incident ray, that incident rays makes a angle phi, that perpendicular angle, okay, it makes angle phi that will be greater than the critical angle. Then and then your light will be reflecting from this. So we have seen earlier the ray theory, in which we say that if that angle is not a critical angle, if it is less than the critical angle, in that case your light will be propagating inside the cladding layer. Right now it is greater than the critical angle, so that's why it will be reflecting from this particular boundary here. Now, if we say that here that light is propagating, okay, it makes an angle of that incidence is about likewise, okay, whatever the phi we say. And sometimes what happen, some light rays are propagating through the axis. It does it no, it will not making any, what you can say, no angle, it may not make any angle, it will directly propagating through the core of this particular axis, Okay, that core we have means at the center of this particular fiber, this core of the fiber. So in that case, if it is propagating at the core axis, light is propagating at the core axis, that rays or that particular light rays, or you can say that that particular incident ray, we can say that it called as a meridional ray. Okay, which is what we can say that rays are propagating at the axis. It is called as a meridional ray. It is called as a meridional ray. Means because that rays are propagating at the center of this particular fiber. So that's why it is called as a meridional ray. Now we consider here earlier that is a ray theory. In a ray theory, we have mentioned that a light is propagating. Okay, the ray theory we have seen that a light is propagating whatever the boundaries of what we can say n2 and a n1 here. In that case, a n2 is greater than the n1 at this particular boundary. When we can say that a light incident, okay, if that incident light is greater than the critical angle, okay, that phi is greater than the critical angle, then it will be reflected back. Now same thing we are learning. Now if supposed to be that angle is not is that angle is not equal to is it is less than the critical angle likewise. So then in that case it will be refracted through this particular medium. Okay, if it is less than this particular critical angle. Now the same principle will study inside the fiber as well as will study that how your light will be launches inside the optical fiber. Means launching of your light inside the optical fiber. Now we see here the optical fiber. Now this is nothing but what we say here. This one is nothing but your core, and that core that is about the axis of a core. Okay, this one is nothing but the axis of a core, and this one is nothing but what we can say. It is about a cladding. This one is nothing but what you can say. It is about a cladding here. You can mention that a cladding will be mentioned here. It is a core now. Now a light is launches. Okay, now that light is launches inside the fiber here. Okay, means accept our aim is to study here what is the acceptance angle. What do you mean by this acceptance angle? Okay, that we are going to study here. Now, in the case of acceptance angle, we should know that what will be the axis here. Okay, what will be the axis here? This one is about your axis, and for a given particular fiber, if you cut the section of fiber from this particular fiber, we say that light incident light incident inside the particular fiber. Okay, light incidence in that particular fiber. So then when it will reflect that particular light, if that angle, okay, if that angle, it will make a critical angle with this core and a cladding boundary. Suppose I am saying right now, this is about a incident light, and now it makes an angle something. Okay, so right now I am just saying that it is an angle theta now. Okay, it makes an angle theta here. It will be propagating through the fiber. Now there is a boundary, we say a core and cladding boundary. If that angle, okay, if that angle, now I'm just going to draw a perpendicular at this particular center now. Now if this angle, if we say that angle is greater than the critical angle, if it is a greater than the critical angle, then and then your light will be reflecting from the fiber. Okay, likewise, your light will be reflecting from the fiber if it is a greater than this critical angle. So now this is about the incident light. Okay, this is about your incident light. It will be reflecting from the boundaries. But the condition is that this angle is to be greater than the critical angle. This angle is greater than the critical angle. Now, another ray we consider here. Okay, another ray what we consider here. Suppose, okay, suppose now if again another ray we say here. So this one is again another ray here. Okay, this one is about a another ray. And again this angle, whatever we say, in that case, it will reach here, it will be reflected from this. Okay, likewise. Okay, if we have this particular angle there, so it makes an angle that is about a critical angle. And then your light will be reflecting from this. Means what we are saying here, when we launch a light inside a fiber, that rays will make that rays will make with this core and clouding boundary, that angle is a greater than the critical angle. Then and then your light is propagating through the fiber. If supposed to be I am saying that, now instead of that, suppose I say that this is again another ray. Okay, okay, this one is about another ray. I'm just going to consider. It will reach here. Okay, now it will reach here. Now when we take a perpendicular here, and this angle is greater than the critical angle, so then light will not be reflecting here. Light will be propagating through the fiber here. Okay, so means we can say that light will be propagating through the this particular cladding layer. But right now what happened? This red ray line. Okay, because this light, incident light, makes the angle across this particular boundary that will be greater than the critical angle, then and then it will propagating through it. But now it's supposed to be another ray. I am saying it makes this angle which is it is greater than that critical angle, then it will be propagating through the cladding. It is not propagating through the core now. So now then this rays, okay, whatever we can say, this rays, this will be that rays whichever is propagating through this particular cladding, so it will be lost. This way, whenever it is propagating, whenever that ray is propagating through this particular cladding, it will be lost, eventually lost through this by this radiation inside this particular cladding. Okay, that is nothing but a loss of fiber. Now, supposed to be, I am saying that another rays I am just consider here this particular ray now. Okay, similar here. So in that case, when it reaches here, when it reaches here, so if that ray is not making that angle, this angle that will be a greater than the critical angle. So in that case, what happen? Again, it will go here. Okay, so means it will be moving and then it will be lost anywhere. Now this is nothing but a loss. Okay, loss by the radiation. Or you can say that whatever the ray, the signal will be lost here. Okay, that ray will be lost. So now that is a part of a loss by this particular angle. Okay, but if it is not a that particular angle, means that ray is to be making at this particular boundary, it is to be a critical angle, then your light is propagating through the fiber. So here, so within this particular range, this is about a range here. So in that range, if supposed to be any ray will okay move inside this particular fiber, it makes an critical that angle phi be greater than that critical angle. So any rays propagating through the fiber, likewise I am supposed to be draw here. Any rays propagating through the fiber that will makes here inside this particular fiber with this particular perpendicular, it makes that angle phi that will be greater than the critical angle. Then and then your light will propagating through the fiber. So this particular angle, okay, this particular angle in front of this particular fiber is called as a acceptance cone. Okay, it is called as a acceptance cone. What we can say? It is about a acceptance cone, or we can say that this particular angle, okay, from the center of the axis toward this particular ray is called as the acceptance angle. So this theta A, we say it is about a theta A. Theta A is nothing but what? We can say it is about a acceptance angle. It is called as a acceptance angle. Now here, what we have learned here, this figure, what it is saying, it indicates that acceptance angle when launching a light, okay, launching a light inside the optical fiber, launching a light into an optical fiber. Okay, that is about your figure. So means we are getting that much is the acceptance angle. So now our aim is about to calculate that what is the value of this particular acceptance angle. Okay, what is the value of this particular acceptance angle that we have to learn. Now this rays, okay, whichever the portion we have indicated in terms of red here, that is nothing but that will propagating through the fiber. And if we put a source, if we put a source at any place, supposed to be I have put a source here now. Of if supposed to be I am here, okay, at any places, but whichever the rays coming from this particular source, it makes it that angle that of light it greater than that critical angle, then it will be propagating through it. So means for a given particular source, if it is a laser, okay, single light comes here. But if it is a LED, so light will be likewise. That light rays will be likewise. So now, for a given particular fiber acceptance angle, supposed to be this, so only the rays that will be accepted by the fiber, which belongs to this acceptance angle of the fiber, which belongs to the acceptance angle. And other rays is nothing but a loss. Okay, that is loss or whatever the incident light from this particular fiber is lost. So that's why. So we need to keep the position of the fiber and the source in such a way that maximum light will be incident, or we can say that maximum rays will propagating through the fiber. So that distance between that source and a that fiber is to be nearer, so that maximum light will be insert inside this particular fiber. So we should know that what is the angle, radiation angle, or can say that radiation region of this particular source. Okay, that we need to be learned. So we see that source later. We just remember that acceptance angle. Okay, that is about acceptance angle of a fiber. Means whichever the light is propagating through the fiber, that makes that particular incident light, that makes that particular ray angle, that angle is greater than the critical angle, then and then your signal is propagating through the fiber there. That is called as a acceptance angle. So you should remember that always. What do you mean by this particular acceptance angle? Okay. Next we see here. Okay. Next we can see that a numerical aperture. Okay. Now we will see that a numerical aperture. So numerical aperture means what? That is about a how much is the how much is the light accepted by this particular fiber. Okay, that how much is the light accepted by this particular fiber, and that angle. Okay, that angle and relationship between this particular incident light. Okay, that incident rays from this whatever the source, and that relationship between that angle makes with this particular rays with this respect to that axis, or it makes a critical angle. Okay, that we need to be learn here. Now we see here a numerical aperture. The numerical aperture gives us the range. Okay, This will give us a range of that particular incident light will fall, or that light propagating through the particular fiber then. Now again we need to learn here this about your core of a fiber. I redraw again here, and this is nothing but your axis here, fiber core axis, and this portion is nothing but the cladding now. Okay, this particular portion is nothing but the cladding, and we say that this one is the N2 and this one is the N1 here. Okay, if we supposed to be say it is about N2 and N1, so N1 is greater than the N2. Okay, and at some particular point, that is about a, this one is nothing but a portion of a core, and this is the axis of this particular core. Now when a light incident, okay, now this particular incident light, then it will be propagating through the fiber here. Then because of that angle is greater than the critical angle, then it will be reflecting. So likewise, your light will propagating through the fiber, and at this particular boundary, we say that this angle is greater than the critical angle. But we say that a light is launching, so means we have a source here. At this particular place, we have a source. So means source is there, that light is propagating through the fiber, and that light rays, whichever the light rays coming from the source, light rays coming from the source, it has some particular medium. That medium is nothing but what we can say it is about air. So air, then it has some particular values of a refractive index. It has a value of a refractive index. Now, according to the Snails law, according to the Snails law, if you see here, so means that this ray, incident ray, it makes an angle with the axis that is nothing but a theta 1. And I supposed to be consider that when it will go inside this particular fiber, it makes an angle with a theta 2. Okay, with the axis itself. Means at this particular case, if I turn here, okay, if I turn here, so means we say that this angle, this light is propagating through the fiber from this particular medium to the another medium, it will be refracted. Likewise. Okay. Now here what? It is to be reflected. If you consider the boundaries of this core and cladding, it will be reflecting. But here it will be refracted. So means there may be a difference in that theta 1 and a theta 2. Always. It is not a straight. Okay, it will not be a straight. What we have learned earlier is that light is ray propagating, it makes an angle greater than the critical angle, then it will be propagating this way. So light is there, instant light is there. If it is not making that critical angle, then it will be refracted. But at the condition of this particular boundary between these two medium, we are just looking for this boundary between these two medium. Okay. Now here what we have learned, whatever the light incident here, okay, incident here, when it reaches here, so it will make that whatever the incident light, it will make that angle is greater than the critical angle, then and then it will be reflected. But some of the light, it is not making that angle greater than the critical angle, so it will be lost. Now this particular portion is a, we just say that light is what will be the acceptance cone of this particular fiber, so which light or whichever the light, okay, that particular region, in that particular region, that light will be incident inside this particular fiber, so that it will be reflected. That is about the acceptance angle. Now here what we are learning that the rays is there, Okay, ray is propagating through this. Now, in this case, what we are learning, the ray is propagating through the fiber. Okay, it makes a critical angle, and then it will be reflected here. Okay, it will be reflected. So now that ray maybe belongs to the acceptance cone of this particular fiber. This ray maybe belongs to the acceptance cone of this fiber. Then and then your ray will be propagating through the fiber. If it is not belongs to the that particular cone, acceptance cone, then your ray will not be propagating through the fiber. Okay, simple. Means if supposed to be I am saying that, so now this one is nothing but a cone. Okay, now I'm just going to consider that this is nothing but a cone. So whichever the rays propagating to the fiber in that particular cone, it will be propagating inside the fiber. Okay. Now this we use a Snails law. Using a Snails law, this one is the another medium that is about air, and this one is the another medium that is about a core. This one is nothing but a core, and it has a core has a refractive index N1 and cladding. This one is about a cladding. This one is about a core here. Okay, if you see that. Now using this particular Snell's law, we can write that N0 is N0 sine of theta 1, N0 sine of theta 1 with respect to whatever the N1 sine of theta 2. N0 sine of theta 1 is equal to N1 sine of theta 2. Now we consider that this ray here is nothing but a phi. This angle is nothing but a phi. And that angle phi, which is greater than the critical angle, we can say that phi is greater than the critical angle. Then and then phi is greater than the critical angle. If that phi is greater than the critical angle, then and then light is propagating through it. So what is the value of this particular phi? Phi is nothing but what? If you use the right angle triangle, this one. Okay, if you consider that right angle triangle here, okay, so in that case, phi will be what? Pi by 2 minus theta 2. Okay, that phi will be what? Pi by 2 minus theta 2. So we consider here that n0 sine of theta 1 is equal to n1 sine of theta 2 now. Now, if instead of that, we write that equation, okay, in terms of what? In terms of a phi. Okay, instead of writing the equation in terms of a, what you can say, in terms of a theta 2, we can write in terms of a sine of, so that theta 2. Now consider that a theta 2 is equal to what? Pi by 2 minus phi. Okay, so I just consider that n0 is equal to n0 sine theta 1 is equal to n1 sine of, okay, that theta 2 is equal to what? A pi by 2 minus phi. Okay, pi by 2 minus phi. So sine of pi by 2 minus phi is nothing but a cos phi. Sine of pi by 2 minus phi is nothing but a cos phi. So we can rewrite the equation n0 sine of theta 1 is equal to n1 cos of phi. Now we simplify this equation. Okay, we'll simplify this equation. We have this equation for what? This is in terms of a sine. This one is in terms of a cos. Now we need to rewrite the equation in terms of a sine now. Okay, either in terms of a sine or either in terms of a cos. So we can use the relations of a that whatever the trigonometry there, you know that a rule of a trigonometry, or a, we can say that sine square, we can say phi plus cos square phi is equal to 1. So means this cos is nothing but what? 1 minus sine square phi raised to 1 by 2. So we can rewrite the equation again. We say that n0 sine of, that is about a theta 1, is equal to n1 1 minus sine square phi raised to 1 by 2. Okay. Now we consider the condition of a limiting case. Okay, condition of a limiting case. This theta 1, okay, that theta 1 is nothing but that limiting case condition is what? It is equal to the acceptance angle of this particular light ray. So means we can write that is nothing but what we can say limiting case, in a limiting case, okay, or you can say that condition of a limiting case, okay, the case of a condition of a limiting case. So now this equation we are getting, that is a n0 sine theta 1 is equal to n1 of 1 minus sine square phi raised to 1 by 2. Now in the condition of what? A limiting case, in terms of what? In terms of acceptance angle. In terms of a acceptance angle. What is the acceptance angle? We say it is about a theta a. Okay, acceptance angle is nothing but a theta a now. Now in the case of acceptance angle theta a, if we write that theta 1 becomes a theta a. Now this is about a accept angle. That is the light is propagating and that ray, it makes an angle with the particular axis, that is about a theta a now. Instead of a theta 1, we'll write a theta a. So in that case, what we can write? We can write that n0 is equal to n0 into sine of theta a. N0 is equal to what? We can write it is about a sine of a theta a. Now, which is equal to sine of theta a, which is equal to what? That's n1. Okay, we can rewrite here that is about a n1 in bracket of 1 minus sine square phi raised to 1 by 2. Now we have seen that earlier the case, that is a sine phi is equal to n2 by n1. Why sine phi is equal to n2 by n1? Because we have seen earlier in the case, okay, that is earlier case. Earlier we have seen that sine of phi is equal to n2 sine of whatever the angle. That angle we consider that is about a 90 degree. Okay. So in that case, a sine of phi will be n2 by n1. Okay. That is nothing but a n2 by n1. Now in this case, if we rewrite the equation sine of phi is equal to what? N2 by n1. We put that here. Sine of phi is equal to n2 by n1. Then this equation, okay, then our equation becomes what? N0. Okay, we say that earlier equation n0 sine of theta 1 is equal to n1 into 1 minus n2 by n1 bracket square raised to 1 by 2. This is about a n2 by n1. If we solve it, n0 sine of theta a. Instead of writing, we are writing the acceptance angle theta a. In that case, n1 raised to what? It is about a n1 square minus n2 square divided by n1 square raised to 1 by 2. Now simplified it, this will get cancelled. Okay, n1 get cancelled. So we have at the end that equation will be what? Sine of theta a is equal to n1 square minus n2 square raised to 1 by 2. Okay, and this one is n0. Okay, we say that n0 is belongs to the medium. Which medium? N0 is the what? That is a refractive index of whatever the medium. What medium? That refractive index of medium. That medium is what? It is about air. So for this air, it is approximately we consider it is a 1. Then our equation becomes sine of theta a is equal to under root of n1 square minus n2 square. Okay, sine of theta. Okay, because we consider that it is about the air medium. So n0 for air. For air, n0 is equal to approximately equal to 1. So that's why we can say that sine of theta is equal to under root of this one. And that is equal to sine of theta a is equal to what? A numerical aperture and is equal to what? n1 square minus n2 square. Okay, and this is nothing but a numerical aperture. Numerical aperture of the fiber. Okay, this is about a numerical aperture of a fiber. Now here we have obtained this numerical aperture of a fiber. Okay, this numerical aperture of a fiber, or can say that that is about a, we can say that numerical aperture, or we can say that is about a, what will be the angle here, acceptance angle of this given fiber. Okay, what will be the acceptance angle? So means numerical aperture will provide you the what is the condition of that particular ray propagating through the fiber. So generally all this, in all the cases, we consider that to obtain this numerical aperture of a given particular fiber, so it is to be related with the air medium. Why it is related to the air medium? Because a light is considered somewhere here, and then from that light source to the fiber, that medium is the air. From the source to the fiber, that medium is the air. So that's why that numerical aperture is considered with a fiber. It is in the air, and that air is have the refractive index that will be equal to 1. So numerical aperture is equal to, generally we say that it is about only a sine of theta a, and that theta a and this theta a is nothing but the acceptance angle. Okay, and this theta a is nothing but the acceptance angle. Means whichever the ray which is propagating from the ray whichever propagating from the range of what, 0 to theta 1 to the theta a. Means what? Here, this one is about your core, this one is about your cladding, and this is nothing but acceptance angle. So this is axis now. Now the ray which is propagating through fiber, it makes an angle that is about a acceptance angle theta a. So from this particular case, another case here we say it is about a theta a from this axis only. Means overall, whichever the ray that will be propagating in this given this angle, even it can be a meridional ray also. Even it can be a meridional ray. That will be in the range of what? From this to this, that is from the 0 to theta a. From the 0 to theta a. That will be propagating through the fiber here. Okay, that will be propagating through the fiber there. So We can rewrite that equations again, that is a numerical aperture, that can be written in terms of a relative refractive index difference between the core and cladding. That is a, what is the relative difference in a terms of a core and cladding? That relative difference, or you can say that a refractive index difference of a core and cladding. Now we say that the ray which is propagating, that light ray is propagating through the fiber, that ray will make an angle from, that will be in between the range from the 0 to theta a. Means what? From this particular range. If it is beyond that, no. If it is in between that the angle, then light ray is propagating through the fiber. Even if that ray can be a meridional ray. Meridional rays means what? It will be propagating through the axis of the fiber. That is called as a meridional ray. So now we can write a numerical aperture in terms of a refractive index difference. Okay, we can write the numerical aperture is nothing but what? A refractive index difference. Del is nothing but what? A relative refractive index difference. Relative refractive index difference. So in that case, we can write del is equal to n1 square, sorry, n1 square minus n2 square divided by twice of n1 square. For this difference, for this particular difference, if it is very very less than 1, then del is approximately, del can be approximately rewrite in terms of what? N1 minus n2 divided by n1. In that case, n1 of del is equal to n1 minus n2. Okay, n1 minus n2. Now in the case of this numerical aperture, as we say that, okay, that numerical aperture, we say that it is equal to what? N1 square minus n2 square bracket square there. Okay, now we can rewrite this n1 square minus n2 square in another way. What do we can write? We can write n1 plus n2, n1 minus n2. That is the repeated numerical aperture here. If we simplify it, because if you consider that this first term here is about a first term, and this is nothing but a second term now. In the first term, if you consider that n1 is approximately equal to n2, n1 is approximately equal to n2. Okay, in this particular case. So in that case, what will happen to this first term? It will be twice of n1. This will be a twice of n1. And we know that earlier, we know that earlier that n1 minus n2, this one is about a second term here. N1 minus n2 is nothing but a n1 of a difference here. Okay. So in that case, we rewrite the numerical aperture. What is the first term? First term is what? Twice of n1. What will be the second term? Second term will be n1 and del here. Okay, n1 and del. So we will get that. We'll get that numerical aperture, that is about a n1 and in bracket twice of del. So means we can say that Na is equal to what? Numerical aperture is equal to what? N1 square minus N2 square is equal to N1 under twice of del. So means we can calculate that numerical aperture either using the two refractive index difference, that two refractive index, or we can consider that whatever the relative refractive index difference of this particular fiber.